Ever try to read code you wrote, a while back and think, wait, did I write this? This is like looking at hieroglyphics.
Uh-huh. Yeah, we've all been there. Code can definitely feel like its own language sometimes, especially after some time has passed.
It's easy for us to get lost in those lines of code, but computers need a way to make sense of it all, and instantly. That's where today's deep dive comes in. We're taking a look at the fascinating world of abstract syntax trees, ASTs for short.
Sounds a bit intimidating, right?
Definitely can seem that way. Luckily, you provided us with some really intriguing articles and research on this very topic, and I'm excited to unpack them all with you and see what we find.
Sounds good to me.
So let's just jump right in. What exactly is an abstract syntax tree?
Okay, so imagine this. You take your code, right, and you feed it into a machine. And instead of spitting out like a snack or something, it spits out a family tree.
Yeah.
But instead of your crazy Uncle Steve, it's showing you all the pieces of your code. Variables, loops, functions, all arranged, all neat and tidy. That's basically an AST.
I've started to get it.
And it's called abstract because it gets rid of all the stuff that's important for us humans, like punctuation and extra words, and just focuses on the crucial parts and how they all connect to each other.
So it's more like a simplified blueprint of my code rather than the actual code itself?
Yeah, precisely. And just like, say, a contractor would use a blueprint to understand a building, a compiler uses an AST to understand and translate your code into something a computer can actually work with.
That's a great analogy. Now, these articles you provided mention lexing and parsing as being super important in building this tree. And honestly, those words sound a bit intimidating at first glance. Can you break it down for us?
Okay, so think about it like reading a sentence, right? Lexing is like reading each word one by one. Parsing, on the other hand, is figuring out how those words all fit together grammatically.
Okay, so it's like breaking down the code into smaller, digestible chunks.
Exactly. The lexer scans your code and it picks out each individual element, keywords, operators, variables, all that good stuff. We call these tokens. They're like the words of your code sentence, if you will.
Makes sense.
And then the parser steps in and it figures out the grammatical structure of those tokens. Like, is it a question, a statement, or a command, that sort of thing.
So if I'm understanding this correctly, the lexer gives us all the building blocks, the words, and then the parser swoops in and figures out how to put those blocks together to create meaning. And that ultimately creates our AST.
You got it. You hit the nail on the head. That's the beauty of it all. The lexer and parser work together. They transform this string of code into something structured and understandable for the compiler.
It's like they're translating our code from something that makes sense to us into something the computer can actually process. That's incredible.
It is pretty amazing when you think about it.
Now, these articles also mention some other pretty cool things you can do with ASTs, not just for compilers. One that I thought was super cool was clone detection.
Oh, yeah, that's a fun one.
Can you tell us a little bit more about that?
Basically, since the AST shows the core structure of a program, you can compare the ASTs of two different pieces of code and see if they're similar, like eerily similar.
Hold on. So you're saying I could take my code and compare it to like a massive code base somewhere, and an AST-based tool could tell me if any sections are basically the same.
Yep, pretty much. It's really useful for finding code that's been copied or, plagiarized.
That's incredible.
That's the power of ASTs, though. They give us a really precise way to analyze and understand code, and that opens up all sorts of possibilities.
My mind is already blown, and we're just getting started. But let's maybe switch gears a bit and talk about how ASTs fit into the world of compiled versus interpreted languages.
Yeah.
Yeah, I always hear those terms thrown around, compiled languages, interpreted languages. And I have to admit, I could use a little refresher on what that actually means in practice.
Yeah, for sure. It's a pretty fundamental difference in the programming world. Think of it this way. A compiled language is like having a recipe, and you have that recipe translated into a different language beforehand. But an interpreted language is like having a chef right there with you who can translate and execute the recipe line by line as you go.
Okay, so with a compiled language, you've got that pre-translated version ready to go, which makes sense why it runs faster.
Exactly. Like languages like C++, Go, Rust, they all use this approach. They have what's called a compiler, and it takes that source code that you wrote and it transforms it into machine code. That's the language that your computer's processor actually understands.
So where do ASTs come into all of this? Do compiled languages even use ASTs?
Oh, absolutely. In fact, the AST is like a crucial step in this whole compilation process. So the compiler first takes You use source code and it generates an AST from it.
Okay.
And then it analyzes that AST. It might rearrange things, it might optimize some things, trim out any unnecessary bits.
Like trimming the fat.
Exactly. And then finally, it uses that refined AST to generate that final super efficient machine code.
So the AST is like the compiler's roadmap to building that optimized, pre-translated version of the code.
That's a great way to put it, yeah. That's what ensures that the final machine code is accurate, but also as efficient as possible. Kind of like, if you're using a map to figure out a route before a road trip, you want to optimize the route right, you want to avoid any traffic jams, maybe take some scenic shortcuts, find the fastest paths. That's what the AST helps the compiler do.
Makes perfect sense. Now, what about those interpreted languages? Where do ASTs come into play there?
So with interpreted languages, things happen a little bit more on the fly. The AST might be generated and used right there in real time as the interpreter is executing the code line by line, but it still plays a vital role. It helps the interpreter make sense of what your code is telling it to do.
So it's less about that pre-translation and more about real-time understanding with interpreted languages.
Right, like Python, JavaScript, Ruby, these are all examples of interpreted languages. They're often a lot more flexible because you can just make changes to your code and then see the results instantly without that separate compilation step. It's like having a conversation with the computer where you can make adjustments on the fly.
So there's definitely a bit of a trade-off there, speed versus flexibility when you're choosing between a compiled versus an interpreted language.
Yeah, you hit the nail on the head. Compiled languages, they usually run faster because they've had that time to be optimized beforehand. But interpreted languages, they give you a lot more agility. They're often a lot easier for beginners to learn, too.
It's fascinating to see how these languages work behind the scenes. But let's circle back to those ASTs. We've talked about compilers, we've talked about clone detection, but what are some other surprising things that we can use ASTs for?
It's really fascinating when you think about it, just how many things you can do with an AST. And it really all comes back to the fact that it's a structural representation of your code. That opens up a world of possibilities.
Okay, give me an example. What else can you do with it?
Well, imagine if you could just automatically generate documentation for your code.
Oh, that would be amazing.
Right. That would be
Yeah.
incredible. And you actually can. By analyzing the AST, you can extract all sorts of information about your functions, your classes, your variables, and then use that to automatically create documentation that accurately reflects what your code is actually doing. Then you don't have to spend hours and hours updating it manually every time you make a little change.
Hold on. You're telling me I could write a program, analyze its AST, and it could spit out documentation for me that actually stays up to date.
That's the idea.
Wow. That would save so much time.
Right. And that's just scratching the surface. We can use ASTs for code refactoring, too.
Code refactoring. I've heard that term, but I'm not sure I fully understand what it means.
So imagine you're renovating a house, right? But you don't want to change how it looks from the outside.
Okay.
Code refactoring is kind of similar. You're restructuring the existing code without changing how it behaves externally. You're just improving the code's internal structure, its readability, without actually changing what it does.
So it's like giving your code a makeover to make it cleaner, maybe more efficient under the hood.
Exactly. And ASTs are super valuable for code refactoring because they give us this really precise and controlled way to make changes to the structure of our code. So instead of having to manually hunt down every single instance of a variable or a function call, you can just use the AST to make those changes globally, and you can do it in a way that ensures that the code's logic is still intact. It's incredibly powerful.
That does sound powerful. But it gets even more mind-blowing than that, right? Did you say something about using ASTs to actually generate code itself?
We can, and it's actually a really cool concept. Imagine you define a set of rules, or maybe like a higher level description of what you want your code to do.
Okay.
You can then use those rules to generate an AST. It's almost like you're building with code blocks. And once you have that AST, you can generate the actual code in any programming language that you want.
So you're saying I could theoretically program in one language
Right.
and then use ASTs as like a middle step to generate code in a totally different language.
That's the idea. It's a pretty wild concept when you think about it. It's being used for things like creating what are called domain-specific languages.
Wow.
Or even building tools that automatically generate boilerplate code, which can save developers a ton of time and effort. It's almost like having a universal translator for code.
That's incredible.
Yeah.
It's really amazing to see how these like seemingly abstract concepts can have such tangible, impactful applications in the real world. Speaking of which, do you have any specific examples of how AST keys are being used in actual software development tools or projects.
Yeah, it's easy to get caught up in the theoretical side of things. Are there any real-world examples of where ASTs are actually being used?
Oh, tons. Once you know what to look for, you'll see them everywhere.
Okay, like what?
Well, think about code editors, like the tools that we use every single day to write code.
Right, our IDEs.
Exactly. Many of them, they use ASTs behind the scenes for things like syntax highlighting,
Oh, okay.
auto-completion.
Wow, yeah. Even error checking, all that stuff.
That makes so much sense. I always wondered how my code editor can, like, understand my code as I'm typing and, make suggestions or flag an error in real time. It's
Right.
almost like it's reading my mind.
Exactly. But it's not mind reading, it's ASTs. It's building up this AST of your code as you're typing so it actually understands the structure and the meaning of what you're writing, which lets it do all those really cool things that make our lives easier as programmers.
That's amazing. It really is like having a silent coding partner. It's always just one step ahead of you.
Totally. And it goes beyond just writing code, too. Think about those code analysis tools, the ones that help us catch potential bugs or security issues, even just style violations in our code.
Right, right.
A lot of those tools use ASTs to really understand what our code is doing and pinpoint any areas that might need attention.
So they're not just like looking for specific patterns. They're actually understanding the code's intent.
Exactly. It's like having this whole team of code reviewers who can examine your code from every possible angle and give you feedback, but it happens much faster and it can be way more thorough.
It's incredible to think that we've gone from compilers and code editors to automated documentation, plagiarism detection, even code analysis tools, and it's all powered by these, seemingly simple ASTs.
And that's the beauty of it, right? They give us this really powerful lens through which we can view, understand, and actually manipulate code in ways that we never could before.
It's amazing. I definitely feel like I'm looking at code in a whole new light. Like, I
Yeah.
used to think of it as just lines of text, but now I see it as this, like, structured, interconnected web of information.
Exactly. And that's really the big takeaway I hope people get from this deep dive. Just understanding the concept of an AST, I think it unlocks this deeper understanding of how programming languages work, and I think it can even help you write better, more efficient code in the long run.
This has been an incredible journey. You've given us so much to think about. Before we wrap up, do you have any final thoughts you want to leave our listeners with?
Let me see. How about this? As we keep building more sophisticated programming languages and tools, how do you think the role of the AST will change? What new and interesting things will we be able to do with ASTs in the future? It's something to think about.
That is an excellent question and a perfect note to end on. If you've enjoyed today's deep dive into the world of abstract syntax trees, be sure to check out the show notes. We'll have links to all the fascinating articles and research we talked about today. And until next time, keep those ASTs in mind and happy coding.